Let's get started. So it's my great pleasure to introduce my colleague, Ted Yoder, today. Let me tell you a little about him before he takes it away. Um, Theodore J. Yoder received his PhD from the Massachusetts Institute of Technology in 2018 and has been a research staff member with the quantum computing group at IBM's T.J. Watson Research Center in Yorktown Heights since then. His interests include quantum algorithms and quantum error correction, with a focus on novel error correcting codes and architectural considerations for practical usage. And I'm sure you and me alike will have plenty of questions for him, so please drop those in the chat when they occur, and I'll either ask him to clarify something on a slide, or I'll save it for the end when we have some time for questions. So with that, Ted, please take it away, and thanks a lot for being here.
Yeah, thanks a lot, Nick. Thanks a lot for having me. Hi to everyone. It's great to have such an international audience, and thanks for staying up late for this, if it's late for you. Yeah, so this is sort of the companion talk to Nick's Qiskit tutorial about the most important graph in quantum error correction, and I'm gonna add the S to graph. We're gonna talk about a few most important graphs in quantum error correction. So let's get started here. So the main problem with our quantum computers nowadays is that the error rates are too high. If we compare to transistors in classical computers with our qubits in quantum computers, we have about 23 orders of magnitude difference in the error rates. So this really makes the point that we need, in the long term, some sort of error correction to solve large and complex problems. Because right now, even if you do have error rates of 10 to the minus 4, you're only running circuits of like 10,000 gates before the error rates become unmanageable. So this talk is going to be focusing on quantum error correction, but what actually does classical error correction look like? So we can take some inspiration from that. So in the classical case, maybe Alice wants to send Bob some bit string. So here 0, 1, 1, 0, but there's some noise in between. There's a noisy communication channel, and when Bob gets it, the message is corrupted. So I think often when people look at this scenario and give some example of a classical error correction code, they talk about the repetition code. They say, well, Alice could just send the same message 3 times, and then hopefully Bob gets it and can like majority vote on the bits that he receives in order to decode the message. So this works. This is a valid classical error correcting code. But the sort of implication here is that you need to copy the message that you're sending, which is something we don't like to do in quantum computing because of the no cloning theorem. So there's actually a different perspective of classical error correction that I want to drive home here. And to do that, we'll use this example of the 743 Hamming code. So what do these numbers mean? Well, the 7 means that you're using 7 bits. The 4 means that you're encoding 4 bits, 4 logical bits. And the 3 means that you can detect any fewer than 3 errors. So you can detect 1 error or 2 errors. Or alternatively, that you can correct any 1 error, which is like 3 divided by 2, and then you take the floor of that. So here's what the 743 Hamming code looks like. And you'll learn as I go through this talk that in error correction, we like to draw pictures a lot. So here's my picture of the 743 Hamming code. So every triangle here represents a bit, and Alice is going to send all 7 bits to Bob now. So she's encoding her 4 bits and 7 bits. The gray bits are the actual message she wants to send, so 0, 1, 1, 0. And then the white bits are extra check bits to do the error correction. So the parity checks are the important thing. So the way that we set these check bits is by making sure that the parity along these lines is equal to 0 mod 2. So if we add up the bits along any of these lines, indicated in yellow over here, you get 0 mod 2. So that when an error occurs, such as an error on this check bit, you'll see that some of the parity checks light up. So in this case, just the one parity check lights up, and Bob, when he gets all 7 of these bits, can tell that, oh, most likely this is the bit that was flipped, the check bit. But let's say that one of the message bits flips, then both of these checks light up. So Bob can tell that this is the bit that flipped. And then if the middle bit flips, all 3 of the checks light up. So this is why one error is correctable. You can see that putting one error anywhere leads to a unique syndrome, a unique combination of parity checks that fires. I hope that makes sense. And of course, you can ask any questions in the chat as we go along here. So that was the classical case. In the quantum case, there's another wrinkle, is that quantum errors are a bit different than classical errors. So of course, we have bit flip errors, like we were talking about in that classical case. This is the block sphere, by the way. Hopefully, you're familiar with this. There's the pure states of a qubit lie on the surface, and then the mixed states lie inside. And a bit flip takes you from the top to the bottom. Now, there's also phase flips in the quantum case, which take you around the z-axis. And there's bit plus phase flips, which, well, is a combination of the bit flip and the phase flip. So these are indicated by X, Z, and Y Pauli matrices. And so all of these are, these sort of form a basis of quantum errors. Whereas in the classical case, we just have the bit flips. So you might think that quantum errors can be somewhat analog because we're on this continuous surface, and maybe there's a small error like this rotation by some angle theta, where theta could be really small, and maybe that error is like hard to correct because it's so small. But a key point of quantum error correction is that when we measure quantum parity checks, which I'll explain, I think, on the next slide, when we measure those parity checks, we discretize errors. So we sort of project this analog error, this sort of continuously parameterized error, into some combination of no error and a bit flip error. And then the bit flip error should hopefully be correctable because we're using a quantum error correcting code that can correct that. Yeah, so then the last thing I want to point out is just that these Pauli matrices anti-commute, and this is sort of the principle that we're going to use to detect errors using quantum parity checks. So let's see how that goes. So when we talk about quantum parity checks, really this is this quantum stabilizer code formalism. So here's an exemplary quantum stabilizer code. The stabilizers equal parity checks. That's what you need to know. So here's a 25.1.5 quantum surface code. And it's quantum because we use these. We now use a double bracket instead of a single bracket like for the classical code. So we use 25 qubits to encode one logical qubit, and we can detect any fewer than 5 errors. We can also correct any 2 errors. So it looks like this, where in red we have X-type parity checks, and in blue we have Z-type parity checks. So essentially, the parity checks are operators that you measure, and we'll show later circuits on how you actually measure these. But when you get 0, that indicates no error, that you're in the code space. And if you get 1 from your measurement, then it indicates that there was some error, and it's the job of a decoder or a decoding algorithm to figure out where that error occurred. Notably here, all the parity checks commute. So that means in quantum language that you can simultaneously deduce the eigenvalues of all of these parity checks. And then the last thing I want to point out is that you use the z checks to correct the x errors and the x checks to correct the z errors. I could have also written detect x errors and detect z errors. And essentially the reason why that works is because of this anti-commutation property from the previous slide. So let's look at some examples. So if there's an x error here, then it anti-commutes with these adjacent z checks. And so those indicate an error. Those have value 1 when you measure them. And similarly, if you have a z error here, the adjacent x checks indicate an error. Okay, and here I'm getting, here I'm trying to make the point that correcting, so for the surface code, when you scale it up, the code distance d, which remember indicates how many errors you can correct, d over 2 errors you can correct. If that's fewer than the number of physical qubits that you're using, then that's not always going to be good enough. So what you really want is that if errors are happening on your code with some rate p, then you expect, order pn errors, and hopefully you should be able to correct that. Which the distance argument alone is insufficient to handle. So let's define this logical error rate, which this is the logical error rate in this model where errors are happening with rate p. Then we can decide whether this function piece of L has a threshold behavior or not. So as we scale up the code, the distance goes to infinity. Does this function go to 0? Does it go to 0 at least for some values of p, or does it go to 1? So if it has this behavior where there's like a step where if you're below the threshold t, then your error rate goes to 0, and if you're above that, it goes to 1. Then we say that the code has a threshold. Yeah, so t is called the error threshold. And then this threshold depends on the code that you're using, also the error model, also what decoding algorithm that you're using. So for instance, here is a plot for this z errors occurring with rate p on the heavy hex code, which I'm going to get to next. But in this case, it's roughly the same as the surface code. Yeah.
Sorry to bother you, Ted. I
Yeah.
was wondering if you could clarify what the distance of the code is. I think there was some question.
Right. So the distance really is just a measure of how many errors are detectable or correctable. So if you have fewer than d errors, then it's detectable. And if you have d over 2, and then you take the floor. So if you have fewer than d over 2 errors, then they're correctable. Right.
Right. And I might add that I think of this as being a physical thing, is like how many qubits, like physical qubits, do you need to implement a logical error corrected one as well? And that
Right.
depends.
Yeah. So you can also think of this as how many physical qubits do you need to act on to do a logical bit flip or a logical phase flip. That's right.
All right. Thanks for the clarification.
Yep. Right. So we were talking about this threshold. So here's a plot of the logical error rate versus the physical error rate for a particular code, which I'll explain later. And you can see this behavior where below this point where all the curves cross, you're getting lower logical error rate as you increase the distance, as you increase the code size. And then above that point, you're getting higher logical error rate. So this is emblematic of the threshold error, the threshold error rate. So this is the first most important graph, or not just specifically this graph, but the fact that you can plot logical error rate versus physical error rate, and then you can see a threshold sometimes. And I think this was also said in Nick's Qiskit tutorial. Okay, so now I'm going to move on to essentially the second part of the talk, where I describe our heavy hex code. One of the challenges we face in experiments with our qubits at IBM is that they have fixed frequencies. And if the frequencies of qubits next to each other in the lattice line up in certain ways, so they have certain frequency degeneracies, then when you do our C0 gates, the C0 gates will have a lot of error. So what are some of these degeneracies? Well, if the neighboring qubits have the same transition frequency between their 0 and 1 levels, then you get a frequency collision. Or if the transition between 0 and 1 of the target qubit is like the transition frequency between 0 and 2 divided by 2 of the control qubit, then you also have a collision. So there are a lot of these conditions, and I'm not going to go through each one, but essentially you want to avoid these by setting the frequencies appropriately, if possible. Now, there are also collisions even between next nearest neighbors in the lattice. And so these are things that you also want to avoid. So that leads us to the experimental layout of qubits that we actually have at IBM. So on the left, there's this square pattern of frequencies, which is something that you would use to implement like the surface code, which I showed earlier. So in this case, every qubit has 4 nearest neighbors. And what that means in terms of the frequency collisions that I showed you on the previous slide is that you actually need 5 frequencies to avoid those collisions. Now, in contrast, if we look on the right here, this is the heavy hexagon lattice. So here, you can think of each of these cells as a hexagon with qubits on the vertices and the edges of the hexagon. And here, every qubit has either degree or 3, 2 or 3. So 2 nearest neighbors are 3. And you actually only need 3 frequencies to avoid the collisions. So that's a big advantage. And we can quantify this by looking at something called the yield. So when you actually fabricate the chip, there's some standard deviation in the frequencies of the qubits. Although you try to set them to some value, those deviate. So you can end up with frequency collisions anyway, even when you're trying to set the frequencies to the 1, 2, 3 values over here on the right. So what this plot is trying to communicate is that if you use the heavy hex layout instead of the square layout, you end up with fewer frequency collisions. You end up with greater yield. So you can see that the red points are higher than the black points. The black points indicating the square lattice, and the red points indicating the heavy hex. And around 20 megahertz standard deviation is what we have currently in our fab. So this heavy hexagonal lattice is great for avoiding frequency collisions and increasing our yield. So I'm going to indicate this as important graph number 2. This is a graph in the like mathematical graph theory sense, that there are nodes, there are vertices and edges, and this is very important. Not just specifically this graph, I guess, but the connectivity graph is very important for determining what error correcting code you can actually implement. Okay, so what error correcting code do we actually implement? This is the heavy hex code. Okay, so there's a lot going on here, but essentially there are parity checks that we measure. Here I call them gauge operators because it's a technical term. But so there's X and Z type parity checks. These are supported on the code qubits in yellow. So here the distance 2 code has 4 code qubits, and the distance 3 code has 9 code qubits. Yellow. Okay, so the gauge operators are what you measure. Now, this code is a bit different than the surface code that I showed earlier, in that once you go to distance 3 at least, these gauge operators don't all commute. So for instance, this guy is XX on these 2 code qubits, and this guy is ZZ, so they would anti-commute here. This means that the useful information you get from these gauge measurements is actually only certain products of the gauge operators. And those products of the gauge operators are the stabilizers. So that's in this center panel. I show you the stabilizers of the distance 3 heavy hex code. Right, so the X-type stabilizers actually look like the surface code stabilizers. There are some weight 4 guys and weight 2 guys on the boundaries. And the Z-type stabilizers are actually these long strips, so they're weight 6. They act on 6 code qubits. Those 6. And they're what we call Bacon-Shore type stabilizers. Okay. So I explained the code qubits in yellow, and then the other 2 colors of qubits are just used for the readouts of these parity checks. So I'm going to show some circuits next. And so when you measure these helper qubits, the stabilizer qubit and the flag qubit, you'll learn these parity checks. You'll learn the values of these parity checks, and hopefully that'll give you enough information to correct the errors. So how does that go? So here I'm just going to talk about the D=2 code. So you can see that this D=2 code is like a unit cell of the D=3 code, and then you just combine these unit cells, you translate them around the lattice to make larger and larger codes. So if we just look at this, we get a good idea of how the larger code works as well. Right, so this is the code, and you can see it laid out here explicitly on the heavy hex lattice. And here's the circuit that we use for error correction. And I think this is also what Nick Bronn does in his tutorial. Or actually, maybe he prepares it differently, but this is what we do in our experiments for our paper. So we prepare all qubits in a product state to start with. So each is in just its individual single qubit state, and then we project into the code space. That's this initialize step. So this initialize step is actually the same as the Z-check step. So it's measuring the Z-type stabilizers. And the way it does that is by reading out the eigenvalue into these helper qubits here, which I guess are just indicated W2 for weight 2 qubits. And then what we do in our experiments is we repeat the parity check measurements many times. So So you measure the X check and then the Z check, and this block is repeated. And on the next couple slides, I'll explain why this circuit works. But for now, just take this as granted. And then at the end, we measure out all the qubits. And so this is how we read out the logical information after it's been protected for some number of time steps here in the middle. Okay, so why does the circuit allow us to detect errors? So let's say that an X error occurs here on this data qubit 1. Then it passes straight through the X check. So the C naughts, if the target qubit of a C naught is flipped, that doesn't change the control qubit of the C naught at all. So it passes straight through the X check. But then when we hit the Z check, the X error propagates up to the measurement. And so we see that X error. Okay, so the Z check ends up detecting the X error. Likewise, if we have a Z error, it passes straight through the Z check. But for the X check, it propagates up to the X stabilizer measurement. And so we detect it there. Okay, so the X checks are detecting Z errors and the Z checks are detecting X errors, just as we want. But what happens with the flag qubits? So these are the qubits here, W2 qubits, that are in play when we're measuring an X check, but they actually didn't help us detect Z errors at all. They sort of, they always reported 0 when there was a Z error on the data, at least. So actually what these flag qubits do is they detect errors in the circuitry. So in quantum, we can have errors both on the data qubits, but also on the other qubits as we're measuring the parity checks. So let's say we have an X error here on one of these, on one of the flag qubits, and it occurs at this point in the circuit. Then it propagates both to the measurement and also to 2 places on the data. Okay, so if we have this early X error, it propagates to 2 places on the data. If we have an X error 1 step later, then it propagates to just 1 place on the data, but also flips the measurement. If we have a very late X error, it just flips the measurement and does not propagate to the data at all. So something you can do to fix this error and use the flag information is what we call a deflag correction. So if you see this flag measurement flip, and it turns out, if you see this flag measurement flip and not this other one, this other flag measurement. So if you just see this flag, then what you should do is apply X to qubit to data qubit 3. So you should apply IX on these data qubits. And what this succeeds in doing is it transforms these errors that could occur on the data into these errors instead. And the important thing about these errors is that there's only at most 1 error left on the data. So essentially, if there's 1 error in the circuit, it propagates to at most 1 error on the data. And this satisfies some definition of fault tolerance, where this error on the data can then get corrected in later rounds, or at least detected in this case. Okay, so those are the circuits, and that's how you use the flag information and the circuit information. So I just want to show the complete set of plots for the heavy hex code. You saw the one on the left earlier. This is where there's Z errors and the surface code checks. But then on the right, we have the case where there are X errors, and we're using these Bacon-Shor type checks. Now, the thing about the Bacon-Shor type checks is that there's actually no threshold. So like whatever decoding algorithm you use, There's no like asymptotic threshold, but you can still see that if your physical error rate is low enough, at least for these finite size cases, you are getting some improvement as you increase the code size. So it kind of has this pseudo threshold behavior. So I just want to point that out. Okay. So now I'm actually I'm moving on to the third part essentially of the talk, and this is all about decoding. Okay, so the challenge of decoding is taking these measurement results. I showed you the measurement circuits earlier. Take those measurement results and try to figure out what error occurred. Right. So in general, the information that's available to a decoder is what we call a set of error-sensitive events. So these error-sensitive events are some combination of measurement outcomes that would be 0 if you had an ideal circuit, but there were no errors in the circuit. So therefore, if you see a non-zero value, then it means that an error occurred. So in the circuits that we do, where we initialize some logical state of the error correcting code, and then we repeat rounds of parity check measurements, the error sensitive events are the difference of subsequent measurements of the same stabilizer. So that's what I'm trying to indicate here, where right. So if you look at the z checks, for instance, the difference of this z check and this z check would make an error sensitive event. And likewise, there's this first z check where you initialize, and the difference of that with this z check in the middle is an error sensitive event. So the x check differences as well are error sensitive events. And then in this case, technically, we have initialized to an in this case, the -1 eigenstate, -1 logical eigenstate, but also +1 eigenstate of the x check. So actually, the first time we measure the x check, we expect to get 0. So that by itself is an error sensitive event. Okay, so these are some details, but essentially the difference of subsequent measurements. And then the easier case, at least to draw, is that the flag measurements themselves are error sensitive events. So I think you could have picked that up from my previous drawings of the circuit. The flag measurements are always 0 if the circuit is ideal. So that makes them error sensitive events. Okay, so what do we do with these error sensitive events? Well, they become nodes in what we call the decoding hypergraph. So they're the vertices here. And then when there are Pauli errors in the circuit, those become edges and hyperedges in the decoding graph. Okay, so let's look at an example here. So these are sort of the example cases that we study in quantum fault tolerance. So that is, we look at Pauli errors that happen after the different circuit components. So here there's a C0, and maybe after the C0, we experience a ZX error, where there's an X on the target and a Z on the control. And then you can propagate this Pauli error through the circuit, because the circuit's what's called a Clifford circuit. You can propagate it through the circuit and it remains a Pauli error. And if you do this, you see that this Pauli error propagates such that it flips these two measurements in red. And when you translate that to the decoding hypergraph, that means that it flips these two error-sensitive events. Okay, so because this error could happen, we draw an edge between those two error-sensitive events and say that edge represents this error. Now, there are other errors that could also draw the same edge. So this edge has contributions from different errors, actually. And then I also want to point out that there are some errors that trigger just a single node in the graph. And so these get connected to what's called the boundary node, just so that we actually have an edge representing those errors rather than, well, I mean, if it just triggered one event, we couldn't draw an edge. So we introduced this sort of fictitious boundary node so that we can actually draw an edge. And so every boundary node is actually the same. So you should think of every boundary node as connected to every other one with an edge of weight 0, or you can just think of them as all the same. Some giant boundary node on the outside. Okay, so that's edges in the decoding hypergraph. But actually, sometimes errors occur, and you end up triggering more than 2 error-sensitive events. So here's an example. If there's a ZX error after this C0, then it propagates through the circuit, and it triggers 4 different measurements here, and that translates to 4 different error-sensitive events. So then we draw a hyperedge in the decoding hypergraph. Well, this is why it's a hypergraph instead of a graph. So these hyperedges are interesting because they're actually real. But then there are 2 different decoding strategies. The first of which, the matching decoder, actually ignores the hyperedges. So if you have a hyperedge of size 3, a hyperedge of size 2 is just an edge. A hyperedge of size 3 or more, the matching decoder ignores this. And the reason it ignores it is so that we can make the algorithm efficient. So minimum weight perfect matching is a problem on these graphs where you try to match up a set of highlighted nodes in pairs, and you try to do that using the minimum weight paths. And it's efficient if you're just working with a graph rather than a hypergraph. So this is in contrast to maximum likelihood decoding, which uses all the hyperedges. So that's something that we do in our D = 3 experiments, which I'll explain later. So actually, this is, I've been using hypergraphs and graph for this object, so it shouldn't be surprising that this is the most important graph, number 3. Okay, so yeah, a lot of important graphs today. Okay, so now I'm going to go through our decoding methods for our D = 2 and D = 3 experiments, actually on the IBM hardware. So essentially, this is the overview. You get to choose your algorithm from the left column, and you get to choose some sort of post-selection method from the right column. And these are what we look at. Okay, so we have the matching decoders. So we have the matching decoders, which I explained a bit about, and then we have the maximum likelihood decoding. The post-selection strategies range from no post-selection, where you just keep everything and try to do your best decoding it, to something called full post-selection, where you essentially throw out every case where you detected any error. So the first thing I'm going to explain here is how we do this matching. Okay, so essentially the problem. Okay, I'm jumping ahead already. So this matching decoding, I explained that you match up highlighted nodes along paths of minimum weight, So essentially the problem is to set the edge weights. So what should how should the edges be weighted so that minimum weight, this minimum weight quantity is meaningful. So what you could do is set every edge to the same weight. Every edge gets weight 1. That's the uniform edge weight method. So I'm not going to explain more about that. But the analytical edge weight and correlation weight methods are a bit more complicated. So what you do in the analytical weight method is that you look at this error as I showed earlier. If this XZ error occurs with some probability, then you add that probability to the probability of an edge. Okay, so the probability of an edge is related to the weight of the edge as follows. So the edge weight is equal to minus log of the probability of the edge over 1 minus probability of the edge. And essentially why it's this is that now when you add the edge weights up, you're multiplying the probabilities. Okay, so then the total edge weight ends up being the like log probability of that of those edges occurring. Okay, and right, so the edge probability ends up being a function of the probabilities of various circuit components failing. And we assume that these are just fixed numbers for every component. Like every C naught in the circuit fails with probability PCX. This is like the theorist model of this. So then the question becomes, how do we set these parameters, the probabilities of various circuit components failing? And you could do this from from randomized benchmarking the components, or you could do this by optimizing the decoding. So you tune each of these parameters until the decoder does as well as it can. Okay, so there, yeah, those are two strategies to set edge weights in the analytical method. Okay, so now that was the analytical method, which is like in theory how we expect errors to work, right? So then the big question is, could we learn better edge weights by looking at our actual experimental data? So that's what this correlation analysis tries to do. It's like, rather than assuming the Pauli noise model from the previous slide, let's look at the real data. So here's a schematic of what's going on, right? You take observations from many of your runs of the experiment where you're doing these repeated parity checks, and you plug it into the correlation analysis, and then hopefully you get out some hyperedge probabilities that make sense. So roughly, how does it work? Well, here's a 2-node example, which you can find from this Google paper. So there are just 2 nodes, but that means that there are three edges. There's the edge from node I to the boundary. There's the edge between I and J, and there's the edge from node J to the boundary. And you can write the expectation values. So the expectation that this node is triggered, or this node is triggered, or both, in terms of the probabilities of each of these edges. So that's these equations here. And so what you get from the experiment is some expectation value. Are these expectation values on the left? And then you can solve for the probabilities on the right. Right, so just invert these equations. Now, if you generalize this, you're going to end up with 2 to the n minus 1 equations if there are n nodes, and you're going to end up with 2 to the n minus 1 unknowns. So you can try to solve these equations numerically, rather than inverting it exactly. But this even becomes too hard for n greater than 4. So instead, what we do is we solve these equations on what are called clusters of nodes, where we just assume that nodes in the cluster exist. So clusters of size 4, just assume that these 4 nodes exist, and we just end up with 15 equations, 15 unknowns. Solve that. And then you can adjust the solutions you get from that with solutions from neighboring clusters. Okay, so that's roughly how it works, and I'm not gonna explain more, but you could look at my papers if you want. Right. So just to indicate that this actually is doing something meaningful, here is the case where we're estimating the edge probabilities for the nodes connected to the boundary. Right. So here are all the edges where one side of the edge is the boundary. And if you do this without taking into account the larger size hyper edges, then you end up with negative probabilities here. So I think piece of I is the probability you get out of the correlation analysis, and then the other value is the expectation value of x. Okay. And then there are some analytical values, which are the points. Right, but if you do take into account the larger size hyper edges, then you can get rid of these negative estimated probabilities, and from the same data set, you get better estimates for the edge probabilities. Okay, so this indicates that generalizing procedure is important. The hyper edges are actually real, and this can occur in other quantum error correcting codes too. So I think this is important. Okay, so that was the analytical and correlation methods. Now I'm going to explain how we do some of the post-selection strategies. So obviously the no post-selection is straightforward. Let's just jump to this category 0, 1 post-selection, which is just to differentiate it from the leakage post-selection. Okay, so essentially, I need to explain another property of the decoding graph, which is that every edge is also colored. So if it's colored red, that indicates that if the matching algorithm chooses that edge, then you have to flip the logical outcome. And if it's colored green, then that indicates that you don't flip the outcome. And if it's colored yellow, then it's ambiguous. So it ends up being 50-50 whether you should flip or not flip. And the existence of these ambiguous edges is just because we're looking at the d=2 code here, what's called an error detecting code, because it detects one error, but it can't necessarily correct every single error. So some edges are ambiguous, and so this gives rise to our two post-selection schemes here. So if you do full post-selection, what that means is that if any error-sensitive event is triggered, then you reject the experiment. So this is the most brutal, right? So this is going to cut out as many experiments as you can. And it also leaves you with sort of nothing interesting going on. So any experiments you keep just have zero measurement. You measure 0 for all your already checked. So that means we can't really study decoding algorithms if we're doing full post-selection. In contrast, if we do partial post-selection, where we only throw out an experiment if the matching decoder chooses an ambiguous edge, because otherwise we know how to correct, or at least we do if there was just a single error. So we only need to throw out cases where it chooses an ambiguous edge, so the decoder is allowed to say that it's uncertain. So if we do this partial post-selection strategy, then we're actually keeping interesting cases, and we can look at our decoding algorithms and compare them. So that's what this slide is communicating our final results for the d=2 code. On the left, there's no decoding, and there's either full post-selection or no post-selection. The percentage here is how many experiments are thrown out due to the post-selection. So here we throw out like 25% of the experiments if we do full post-selection. And then also whether we do this deflagging procedure that I talked about earlier or not. Right, so in the full post-selection case, we get error rates for the logical qubit that are below like 10 to the -3, which is even exceeding our physical error rates. If we don't do any post-selection, so this is keeping all the results, and if we match along an ambiguous edge, then we just say that we don't flip the logical. Then we see that the correlation decoder is outperforming the analytical by a bit. And if we look at decoding with partial post-selection, then the analytical is actually performing the best. So these are our results for the d=2 experiment. And now I'm going to move on to the d=3 quickly. we have about 5 minutes left. Here's the d=3 circuit. It's just a bunch of copies of the d=2 circuit. So I'm not going to spend too much time here. But essentially, again, we have a logical state preparation, and then we have repeated rounds of parity check measurements or syndrome measurements, and then finally we end with a logical readout of the state. So what's unique for our d=3 experiments is that we tried out this maximum likelihood decoder. Well, also we tried out the leakage post-selection. So we have to discuss both of these before getting to the results. So here's the maximum likelihood decoder, or at least an overview of it. I'm not going to go into more detail than this, actually. So the input is the set of error-sensitive events that you see, but then you imagine that instead of just doing this perfect matching that the matching decoder does, you actually imagine that you take all the different ways the hyperedges can occur, so that when you add together that subset of hyperedges, their sum is exactly the set of error-sensitive events that you see. So you look at all these combinations that give you the observation that you see, and then each of those combinations also tells you some correction to apply. And then you just choose the most likely correction. Okay, so this is an exact maximum likelihood decoder for circuit noise, which is kind of in the spirit of these two papers, Swarry, Hastings, and also Priagla. So again, the maximum likelihood decoder is taking into account the hyperedges, whereas the matching decoder is not. So we expect improvement. So that's what we see in this experiment on our Kolkata device. This was sort of a preliminary experiment where we compared all the different decoding methods for our d=3 code, and we see that the maximum likelihood decoder is performing the best, and followed closely by the analytic model where we tune the parameters of the noise. And so we tune the parameters so that we're getting the best decoding possible. Okay, so that was the maximum likelihood decoding, which we'll return to for our final results. But now I want to discuss the leakage post-selection. So So what is leakage? So I mean, in our qubits, there are actually more energy levels than 0 and 1. 0 and 1 is used for the qubit, but then the state could also leak to levels 2 or higher. So that's leakage out of the computational space. So there are certain ways to characterize leakage in the device, and essentially these amount to repeating the circuit element many times that you want to characterize. So you can repeat the gate many times and see how often it leaks, right? Or see the rate of leakage. So you get sort of plots like this, where as you repeat the gate, the amount of leakage goes up, and you can fit to this curve, this P leak. And from that, you get the leakage rate, gamma sub L. You also get what's called the seepage rate, which is the probability of the qubit goes back into the computational space. So you can do this for both gates and also for measurements. The measurements you repeat multiple times, just as you do for the gate. So this way you can estimate your leakage rates. Now, this should not. Yeah. Okay. Anyway, so this when we do our experiments, what we want to do is actually characterize a single measurement. So the single qubit measurement gives us some point in this IQ plane, which we can characterize as either 0, 1, or 2. So for instance, we get some plot that looks like this, and the qubit is prepared. So the way you generate this plot is by preparing the qubit in 0, 1, or 2, and then we're measuring it repeatedly. And so there's some mean and standard deviation of the I and Q values that you get for each of these preparations. And so the way we propose to classify a certain measurement is that if I is less than 0 and you're within 3 sigma of the 0 state, so in blue here, then you would classify the measurement as 0. And then if that's not true, you check the second condition. If you're within 3 sigma of the 1, classify as 1. And then you check the third. If you're within 3 sigma of 2, classify as 2. Otherwise, you classify the closest. So why you want to do this multi-step procedure instead of a single step? So like a single step could just be, let's say we want to classify to the closest centroid right off the bat. Well, we do this multi-step because here we're prioritizing the 1 states, which, because we start the qubit in the computational space, we sort of expect there's some prior belief that we are going to remain in the computational space most of the time. And there's great overlap here between the 1 and the 2. So we want to make sure that we're classifying the 1 more often than we're classifying to the 2, because that's just more likely based on our prior belief. Okay. So here's some examples of, if you initialize the qubit, it gets classified to the 0 state most often. After you do a cinder measurement where it's 50-50, whether it's 0 or 1, it's roughly 50-50, 0 or 1. Okay, so this slide is just communicating that when we do this classification method for our rounds of parity check measurement, this leakage classification method, we're getting values that are roughly the same as what we expect from our leakage characterization. Okay, so these are roughly matching up. And this is like the second to last slide, so I know I'm a bit over time, but so here are like our some of our final plots for the d = 3 experiment. here we have the logical error rate as a function of rounds. And essentially by fitting these curves, you can get the logical error rate per round, which is shown in the inset here. If you do post-selection, where we throw out, 4.3 to like 5% of the data, then you actually get improved logical error rates by 2% or 4% in the case where you're starting in logical plus or minus. Okay, and then we can also compare the decoding strategies. So here we have a couple versions of the matching decoder and then the maximum likelihood decoder. And the maximum likelihood decoder is improving over the matching decoders. Okay, so I want to conclude here because I'm over time, but this is my summary slide of the most important graphs in quantum error correction. You can see the logical error rate plot, the connectivity graph, and then also the decoding graph. And you can check out our papers. So thanks for listening, and I'll happily take any other questions.
Well, thank you so much, Ted, for that wonderful talk. That's definitely a fascinating topic, and you've touched on so many aspects of quantum computing. Could I get some applause emojis in the chat and any questions you might have, followed by my first question, which I know has been discussed on the Qiskit seminar series before, which is certain radioactive events, for example, that cause the breaking of Cooper pairs can cause correlated errors across a relatively large region of a quantum processor. And I was wondering what kinds of codes or what kinds of research you're doing with respect to that kind of event.
Oh, that's interesting. So I imagine these events are somewhat localized.
Exactly.
And geometrically local in the plane. So yeah, I mean, I think the error correcting codes that we're looking at here, like the heavy hex code or the surface code, can correct those errors at least if the code is large enough. Here we're just looking at smallish versions, small codes, and if maybe one of these events occurs and it corrupts, it'll end up corrupting a large fraction of the qubits. So it'll be uncorrectable for our small codes here. But as we scale up, these might become correctable. And it sort of sounds like these are more like erasure errors than maybe poly errors. But that's also something that our codes can handle.
I see. So as long as the error is localized, even if it's correlated, you can still correct for it if you have a large enough code.
Right.
Cool.
Yep.
Well, that's good news. Let's see. There were some questions in the chat earlier, so let me see if I can ask this one. Are classical Shannon or Huffman error correction techniques ever used in quantum?
Shannon or Huffman techniques.
I don't know what those are either.
Right. So I think like Huffman coding is trying to come up with like the shortest code for. I mean, as far as I know, like Huffman coding is not really about correcting errors, but maybe the questioner could clarify. So here we're really focusing on like error correcting techniques. I think like the Shannon question. So Shannon has like, or at least the theorem that like you can randomly choose classical codes, and they're going to be good. So quantum codes actually have some additional constraints over classical codes, which we actually saw in our talk. So the like X stabilizers and the Z stabilizers need to commute. So this actually makes the study of like random quantum coding theory a bit more complicated. than classical random codes. Now, there are ways of taking classical codes and converting them to quantum codes. You can look at what's called like the hypergraph product. And in that case, you can use like random classical codes and get quantum codes that are, they do somewhat decently.
Cool. Okay, here's another one from the chat. I got a yes, Huffman codes are more about compression of information symbol than correction of actual errors. So confirmation from the chat.
Okay,
There was another one I kind of answered in the chat because I kind of use Pulse a lot. But the question is there a best way to learn how to do error correction codes work using Pulse, or would it be better? Yeah, that's basically the question. My thought initially was, as far as this is all about Clifford circuits, basically just using Pulse to tune up the best Clifford gates is what's important here. But then I know we've had other chats about driven dissipative systems or control, like of flow K qubits, for example. It's kind of adjacent, not exactly the same kind of error correction work. But I was just wondering if you had any thoughts on that.
right. So something I mean, this is sort of this is adjacent to the question. Something I didn't get to here was that we actually do some like dynamical decoupling as our parity checks are happening. So sometimes there are qubits that are just idling, and so we do dynamical decoupling sequences on those to suppress Z errors that might occur. And this actually makes a pretty big difference for the logical plus and minus states, which are sensitive to these Z errors.
Yeah.
So yeah, I mean, tuning up gates and doing certain pulse sequences to suppress errors is actually an important complement to these error correcting codes.
Absolutely. Error mitigation seems to be, a very hot field, in the noisy near-term era of quantum hardware before we get to the kind of thresholds where we can reasonably do logical encodings, for example. And so you kind of entertain my last question, or my last question is there any kind of like hybrid, kind of like maybe I want to say like partial error correction? Like, would it be useful in certain algorithms to try and error correct, say, idling qubits? I'm just thinking of an example, or any class of qubits in an algorithm that could be, somewhat corrected to get an advantage over not doing any correction.
Yeah, so I think this is getting to like open questions in the field. I mean, it depends on your algorithm, and probably the type of error matters here as well. So I mean, you can imagine that that X errors are more problematic at some points in the circuit than Z errors. Like if you're just before you're measuring out the information, then you don't actually care about Z errors, right? So quantum error correction can be used to suppress just one type of error and leave the other. So if you make like the surface code asymmetric, so you like make it a rectangular code instead, or you can do the same with the heavy hex, then you can preferentially suppress one type of error and leave the other. I think you also brought up error mitigation, and so you could imagine using error correction to suppress errors to some extent, and then using error mitigation on top of that to suppress it the rest of the way. And maybe that's cheaper in terms of qubit cost, because the full-blown error correction is would require a lot of qubits, a large patch of surface code, but then the error mitigation just repeats the same circuit on the same patch of qubits on the same smaller patch, and so you can use that to get the rest of the way.
Yeah, exactly. I think alluding to kinds of areas of exploration that that will be important in these kinds of larger qubit, lower error kind of place between the noisy and the error corrected, where I think, personally, I believe there's a lot of room for exploration in these areas. So I think that's very interesting.
Yeah, we're definitely just in the early stages of experimental quantum error correction, right? These are the smallest codes that you can possibly implement here.
Exactly, as you can see in the little tutorial we put out today as well.
Yeah.
It seems like I think that's all the questions that we have today. I want to thank you so much for that wonderful talk, Ted, and it's great to talk with you again. And I encourage our viewers to like and subscribe to the Qiskit YouTube, and we'll see you next week.
Thanks a lot, Nick.
Take care.